Let's start. Today's discussion is a very open discussion. There's no set plan. So it's basically, I have prepared nothing. It's basically your participation. I'm going to basically summarize the basic facets that I see the Swampland program going, and then you could say what you think we should be doing, or what are your thoughts, or what, just as an open discussion. So I first start by general discussion. So if you view the Swampland program, I think there are various facets to it. One aspect of it is theoretical. Theoretical meaning what? Well, theoretical we can mean by that, first of all, formulating conjectures or statements, criteria for the theory to be good, to be in the landscape, testing it, so this formulating it, testing it. Testing means understanding it in examples like in string theory where we understand what's happening. And then the other part is explaining it. And explaining it is a part that we haven't developed as much, actually. I think there are few ideas already here, but I would say that this area needs, in my opinion, to be growing much more strongly. So here the typical ideas we have been using are black holes, ideas having to do with unitarity, other ideas having to do with studying defects in these theories. So there are some ideas already that go into proving or explaining some of these, but this side needs much more techniques than we have currently.
You mean explaining from a bottom-up perspective?
Right. Without using string theory. Without using string theory. In other words, if somebody says string theory is not the only theory of quantum gravity, there are these other theories, you should be able to say, no, it has this problem or that problem or that problem, this doesn't work, and so on. So this is what I mean. Without using string theory, that's what explaining it means.
Holography you would include?
Holography would be part of explaining in that context. Holography would be a subset of these cases, but for example, it would explain in the ADS context. Maybe it doesn't explain in the Minkowski context. So yes, so I should add holography as another example. So there are ideas here that go into trying to explain it, but I would say that this is still thin really. This side, we have a huge number of decades of string constructions, examples. We have a lot of examples here. And we can so the testing is easy in some sense. Formulating is still, I think, the nice discussion we had, which was led by Irene and Gary the other day, showed that there are still many, but still there may be many more that we haven't understood. And of course, connected to this is unification of these ideas. Is there a unifying principle? So do we have anything which kind of says, oh yeah, this is all the same thing. This is just, and it smells a lot like it's all the same thing. So all these things, criteria sound in some way repeating themselves, and we haven't quite figured out exactly what that means. But trying to unify it is certainly there. Explaining it, of course, would be ideal. That's what we are trying to do. That's what understanding the Swampland criteria would be. Now the testing, the way it has been going right now is that the setups that people have been testing it typically involve, the ones which are more sure about, involve supersymmetry. So theories with 32 supercharges, 16 supercharges, 8, 4, etc. The number of supercharges in the theory, the higher they are, the easier we can make this because we are sure. For example, with 32 supercharges, we know everything. And recently there was progress with 16 supercharges, and there are some statements with 8 supercharges, and there are very little with 4 supercharges, and so on. So the test ground, of course, supersymmetry is a good case to start with. So if we want to formulate criteria, it better pass this subset, at least. We could be misled because supersymmetry could mislead us to some structure which is not generic, of course, but at the very least it should be good testing ground for any statements, would be statements. So this is, I think, a good place of theoretical part is developing the supersymmetric techniques, and I would say that we have a relatively good understanding of these two cases, but this case already, which is the analog of the 4D n equal to 2 systems, we don't have a good testing, we don't have a good criteria. Could we have predicted what are the possible n equal to 2 theories in 4 dimension? Could we have predicted what are the 61,0 theories could have been, a priori, and first tested those ideas and then explaining it based on these. So these are, I would say, the general circle of ideas for theoretical things people have been working on. On this side, I would say that the study, in my opinion, study of the defects and the interaction with the defects has not been explored enough. I think that we know that by completeness of spectrum, there are some states that have to be there, strings, membranes, D-branes, whatnot, just because of the completeness of spectrum. Studying what lives on it, unitarity on them, interactions between them must be a huge constraint on the theory. And some aspects of it was already used, for example, to rule out U1 to the 496 gauge group in heterotics would be heterotic in 10D, which doesn't exist. So those criteria of what kind of statements can be said without using too much about string theory, but generously, I think is crucial. And I think that has to be developed more. So this is as far as the theoretical goes. The other one would be related to phenomenological applications. Now, the phenomenological applications typically involve understanding better the case that is hardest to do, which is the n equal to 0 case, with no supersymmetry, and this would lead to potential applications. Of course, there could be some features of supersymmetric case which also would have phenomenological applications. An example of it is that, for example, there was a paper we studied where the theta angle for n equal to 2 case, so you could talk about n equal to 2 gauge theory, n equal to 2 supersymmetric theories in 4D, and you can ask, are there cases where the theta angle is forced to have particular values, and what are those values? Could this be related to the strong CP problem, the value of the theta angle being so small in the QCD? So in those examples we found, even though we were talking about the higher supersymmetric case with 8 supercharges, we found that theta was either 0 or pi. And it was not forced on by any symmetry like CPT or any C or PRT. Any of those was not the reason for it, but we found that string was giving you 0 or pi only. And there's no explanation of it from string theory. It was just an observation. So there could be phenomenological applications which are motivated by higher supersymmetry just to understand them. But I think most deep applications will come from no supersymmetric case clearly, because we don't have supersymmetry in our world. And there are two kinds of applications we can have: particle physics and cosmology. And the particle physics application could be basically all these puzzles that we are facing in the context of the particle physics, the fine-tunings, the hierarchy, and all that are golden opportunity, I would say, for ideas coming from Swampland. That is, effective field theory is misleading us to think theories which are perfectly normal are not allowed. And that would be potentially a very interesting connection with hierarchy problem. And already there are hints that this may be the case, that in particular the connections between the dark energy and neutrino mass scale seem to be, and neutrino mass scale related to via seesaw to the Higgs mass and all that, suggests that hierarchy may be partly in the game in trying to explain. And the fact that hierarchy has not have a nice solution in the context of typical approaches to effective field theories in particle physics suggests this may very well have an answer in the context that involves quantum gravity, taking into account quantum gravity. Other applications could involve, and related to this perhaps, of studying the dark sector, what constitutes the dark sector and what constraints we have on the dark sector, and also its mixing with our sector. So in this hierarchy we are talking about standard model, and then there are relations to things like neutrinos, the masses of the neutrinos, and the dark sector, and in the middle of it will be related to cosmological question, which could also be related to this, which is the present cosmology, which is the dark energy. How does the dark energy relate to dark sector, relate to particle sectors? What are the relations? We heard a talk by Dieter where the connections between the masses of light states and lambda was discussed potentially. So the powers of lambda being related to the tower of states and this is typically the case for neutrino being related to lambda to the 1/4 is already an amazing statement. So it's again a golden opportunity for us to try to explain in the context of these ideas. Other ideas would be in the context of, again, standard models, and this is something that Miguel mentioned yesterday in his interest, is symmetries. So we don't have the exact understanding of what is the exact symmetry of the standard model even. What's the exact global structure of the gauge group. So the ideas about symmetries and the lack of global symmetries in quantum gravity may very well end up teaching us something more about even the standard model. So I think this would be, again, another opportunity to try to connect to the structure of the standard model and what can we say based on quantum gravity for the standard model. For cosmology, the present cosmology, of course, is a big issue, understanding whether or not we can have this ether. I think that's still an open question. There are the conjectures that suggest they may not exist. Constructions, or would-be quote-unquote constructions, suggest that they may exist, so we don't know the answer yet. Either way, it's very important to study. I think this is one of the important directions of the Swampland, to settle this question one way or the other, and it's critical importance for our universe. Clearly, there's no more urgent question, in my opinion, in the whole string theory research than understanding this. To understand that what is the nature of this dark energy, can it be stabilized, and if so, what are the concrete models where we can understand this in string theory. And the other related to the question of cosmology is the past, early universe, I would say. And in the context of the early universe, the popular model, of course, is inflation. Now, in the context of inflation, again, the same issue, whether or not inflation models of the type that we want in string, that we want to agree with observations, could it be possibly constructed in string theory? People have tried doing that. There are lots of obstacles, and so there's generally difficulties. And so the question is are these difficulties insurmountable, or they are possible difficulties just because they are hard to, the standard, the universe might be difficult to model in string theory, or there are more fundamental problems? At any rate, regardless of whether or not you can embed inflation in string theory or not, it would be important to talk about alternatives. And I think this is embarrassing in my opinion, for our field. We have not studied enough alternatives to inflation. And this is something that I think that the reason I call this embarrassing is because you would expect that might be the era where the brains and the membranes and dynamical objects, which are not point-like, become relevant at the early universe at high energy. And we have learned in string theory that they're unavoidable. They're unavoidable. And somehow to say that early universe is devoid or irrelevant for that is bizarre. It could be like inflation comes and wipes everything out. But it's also possible they are relevant. And so this story, I think, embarrassing for our community not to have been developed enough. And I think that's one area which I think these ideas from Swampland suggest we should try to focus and understand what alternatives we can have to inflation. So this is my general overview of the way I see the subject going. But it's an open discussion. I don't want to dominate, so we can start discussions now. Yes?
Concerning phenomenological aspects, would you agree with the statement that the scale separation conjecture is potentially the most important one? Because if there's no scale separation, let's say for ADS or something like the sitter, what does it mean to do phenomenology, right? Standard model, we clearly assume there is a huge gap with the UV degrees of freedom. But in a lack of scale separation, we should really rethink the whole phenomenology, from scratch.
So we should be careful about that. So if you're thinking about phenomenological application, I would say that we have to know more about dark sector before we can make that statement. So there could be, for example, we could be living in let's say, would be the sitter space with a tower of states which go lambda to the power of some order 1 number. And then you say, well, where is this tower in our universe? Well, it could be part of dark sector. We don't know that. So part of the question you're asking would be related to how much we know about dark sector, and that's why these are related questions. We cannot avoid it. So it might predict that, there must be something going on in dark sector, so we make predictions about dark sector. So all these things are, I think, exciting for our field, to try to get some specific predictions about our universe, and that's what I think is what's missing right now.
Also, the scale separation is for ADS, but for the sitter could be the other way around, no?
Sorry?
The scale separation, the fact that alpha is smaller or equal than 1/2 is for ADS, but for the sitter...
No, the statement was that if we don't know if there is a metastable de Sitter or not. If there were, then the argument that we related to distance conjecture suggests that there are a tower of states whose gap goes like lambda to the power of order 1. We don't know order 1 number, but order 1 number presumably is less than 1/2. We don't know what the value is. 1/4 would match with the neutrino scale. So the tower of neutrino scale-like object as being populating a dark sector would be interesting. Could it be viable? What kind of cosmology does that give you? And so I think these tower of things coming from string theory is extremely, I think, exciting and potentially having impact in possible observational cosmology would be very worth studying, I would say.
But in certain sense, from this string theory approach, you can say that this UV and infrared are mixed, right? Because you can kind of having very low width of wire in certain sense, right? And then the notion of hierarchy becomes a little bit kind of mixed up. I'm not sure how to talk about hierarchy.
Yeah, no, I think this whole thing, I think this, what you're saying is very important. This is precisely the Swampland program, which says that you usually think the IR and UV decouple. So that, therefore, this effective field theory should be good enough. So what are we talking about? The statement that we are learning is that that actually misses the point. So there are mixtures between UV and IR when you bring in quantum gravity. So quantum gravity is unlike quantum field theory. And so quantum field theory intuition that UV and IR physics are decoupled is incorrect.
Yeah.
That's the main point. So, but how does it couple? We don't know exactly how you get the infrared restrictions.
Does it mean that quantum field theory is finished?
No, quantum field theory, well, so let me say it this way. Quantum field theory is not finished for quantum field theory if you exclude gravity. But if you're interested in coupling gravity, n equals to 4 Yang-mills cannot be any better quantum field theory than that. But the rank bigger than the 22 is excluded with quantum gravity. So,
This I understand.
So that already is a strong, so if you say excluded, I would say yes. Essentially all quantum gravities are excluded. Sorry, all quantum field theories are excluded in quantum gravity except the finite set, which string theory is clever enough to discover. So in other words, the intuition that Feynman and others had for saying that field theory diagrams don't make sense and you cannot renormalize it is correct. And it proves essentially all quantum field theories cannot be coupled to gravity. So that intuition which we thought was wrong is actually, in my opinion, correct. There are just some finite number of counterexamples which string theory has discovered. That's the way to look at it. We are very special jewels that quantum gravity works, and that featuring what are these aspects of these jewels that are possible, making it work, is what we have to figure out. That's the task. So it's very difficult to ask, but it's not going to be a generic effective field theory argument. That's false. That much we know. At least that's the whole program.
So I will make a very, very kind of stupid comment on this. I mean, I tried to take the opposite point of view to my usual point of view and work on quintessence. And we wrote a kind of half-negative paper some time ago and didn't get much attention. Then I checked that another paper was written by Dieter Lüst recently. And then I checked the main paper on quintessence and string theory. The best one, I think, is by Kavli and Cumrun a few years back. And I checked, just seeing whether it's my own fault, I checked that their paper actually got 2 citations in that period of time. So, of the 30 total. So I really have the feeling that the community, maybe it's not taking that challenge seriously. I mean, and I don't see any alternative. I mean,
we should. I mean, either we prove de Sitter's constructions or quintessence. We have to do it because otherwise our universe is inconsistent.
Maybe it's neither de Sitter nor quintessence. Maybe there's something that defeats our EFT imagination. But then somebody should work on it. I mean, a suggestion.
I'm 100% with you. I think our community is, unfortunately, if you say the fraction of our string theory working on this is less than 1% or 2%, it's embarrassing, I would say. It's embarrassing.
That was my comment.
But I think the view was, and I think this was the incorrect view, there are 10 to the 500 cases, and anything you write down basically works, so why you waste time on that? That was kind of at least the hidden attitude, that you're not going to learn anything by going and constructing string theory. That was, I think, that to me was the reason that the community was saying, okay, let's go back to doing theoretical things in string theory and not worry about this. Somebody solves it with some compactification.
This may still be true in case the Sitter exists, and this exists in the way we imagine. This may still be the correct attitude. But if you take the point of view that doesn't exist, or some people take the point of view that doesn't exist, then of course the other scenarios have to be pushed at least to that level.
Well, I would say that even if the Sitter exists, even if KKLT is, in some way is correct, I would say that what we are learning from all these is that you're not going to get everything you want. Or everything you can imagine. Understanding exactly what are these restrictions is crucial, regardless. Okay. To me, the Swampland problem is far more than de Sitter or not. De Sitter is the hardest problem we are facing. And maybe that has attracted attention for people who are not thinking about Swampland to start thinking. But I think the program, in fact, I would suggest starting with the highest supersymmetric case, where it's cleaner, clearer, delineating conditions in those cases which are. We have examples, we have much more tools, we have non-renormalization theorems, this and that. In those cases, can we figure out what's going on? Even that. So the statement I just made for 16 supercharges that you cannot get n equals to 4 Yang with rank bigger than 22 is one of those examples. It's completely counterintuitive to a field theory. Why would SU50 be bad coupled to gravity if it's finite quantum field theory? Yet we think it's bad. So those kind of things I would say if we understand what's going on with those examples, I think would be extremely important. So I think, but I think that I agree with you that, and this is, I think, is unfortunate. Even within the Swampland community, I would say that attention on phenomenological things are not as much as it could be. I think there are many exciting things that we could be doing in the context of cosmology, in terms of connecting what's going on in dark sector, motivated by ideas from Swampland, like Tower of States, or the relation with lambda and the neutrinos, and this and that, which is very small compared to the potential impact. So I think that's the area I think that we need to do more work on.
I think so. In the other workshop here at the KTP, people are discussing theories like JT gravity and things like that, that naively would be in the Swampland because they're theory of pure gravity without all the string theory discussion. Or, if you wish, 2D gravities with gauge.
2D gravity. So these discussions about the Swampland are very much geared to the dimension higher than 2. So if you have examples like 4D, then we can, or 3D or something, which is more, that will be more relevant. I don't think they will be in Swampland. For sure, there would be. There's nobody claiming that JT gravity is in Swampland.
Well, but it's a theory that naively, it's the Swampland. It looks a bit like in the Swampland because it doesn't. And furthermore, but what the lesson was that it could be interpreted as coming from an ensemble of theories and so on. That is the proper interpretation of those theories. Naively, you would have thought, oh, maybe it's in the Swampland.
No, we can talk about 2D theories, but let me first of all say 2D.
He hasn't defined the Swampland.
Yeah, I haven't told you. You're defining. I'm not sure why you say it's in Swampland. Who said it's in Swampland?
If you insist on non-ensemble of theories, that defines the Swampland.
Well, it's a change of framework. I think it's a theory that naively does not make sense, and it has some problems. You would say it has some problems. For example, this partition function gives some wrong results if you think that it's dual to a given theory. But it is correct if you think of it in terms of an ensemble of theories. And so one question is, you could say, okay, well, this might be something special about 2D theories. In 4D, it will work differently. But this is a simple theory that we can solve exactly, and this is the lesson we learned from this theory. Right?
Well, I'm not convinced that's the lesson we learn from those theories. So let me contrast what the example you're saying with the Fuzzball picture. So the Fuzzball picture is a lesson some people claim that we should learn about black holes in the context of regular black holes, regular string theory, and so on. And the idea that you also have an ensemble there is perfectly consistent with everything we know about string theory. Nothing exotic was introduced to describe the Fuzzball in the context of string theory. Yet, that's one of the lessons people like Steve and all that suggest that JT gravity is teaching us. So I don't think necessarily JT gravity is teaching you something exotic in terms of what we know.
So, Cumrun, another way of saying it, in the Swampland program might connect to another program,
Yes?
which is looking for UD complete theories.
That is what?
It's looking for finite or UD
Yes.
complete theories of gravity.
Yes.
And that's not necessarily an empty set.
There is a UV completed, for example, ADS cases. The cases where we do ADS CFD are complete theories where we have examples where the gravity makes perfect sense. We have.
No. But those are string theories.
Well, you could. It doesn't have to be a priori, but yes, you could. There's another thing I haven't talked about. I didn't say necessarily, and that's something we can discuss, whether or not every quantum gravity comes from string theory or not. That's something that we could talk about. Here we are talking about the testing ground. We can certainly use string theory because we think those exist at least. Then we can ask whether there's a completion of them, whether it's within string theory, whether you have to enlarge string theory, which is nothing to do with string theory. That's an open question. I'm not taking necessarily a view on that. But some ideas, for example, the theories with 16 supercharges, it could have been that there are theories with n equals to 4 Yang-Mills with SU50, and string theory can only go up to rank 22. Now, there are arguments without using string theory which says, no, rank cannot be more than 22. So it at least suggests that it's essentially complete. Now, it may or may not be complete, but yes, there could be other kinds of complete quantum theory, systems of gravity, which have nothing to do with string theory a priori. That's possible. I'm not ruling that out.
Could it be that one lesson is that theories that naively might be in the Swampland, like let's say 4D gravity plus an axion,
Yes.
Without any potential?
Yes.
Those could be interpreted as theories on an ensemble of all possible consistent theories, and each consistent theory, each full theory, will have some axiom potential, but we take the average over all of them and we get this theory. This is what is happening in this JT gravity.
Well, why are we seeing something like that in the context of supersymmetric theories?
Well, maybe we could. I don't know.
Well, so this is I'm exactly these kind of examples are driving us to say the conclusion is that string theory is not just a lamppost of possible theories that we have been studying. Your view would be in that context, well, you have just studied these very specialized.
No, it might be that with 32 supersymmetries there is a unique theory, but
No, with 16,
even with 16,
it's not unique. We know it's not unique. We know it's not unique. So my point here is that it's not like. It's possible, as I just said today, we don't know what the full set of quantum theories are. We could take the view, look, string theory is a minute set of all quantum gravities which are consistent, and that's all we can study because of the lamppost of string theory. And that could be true. In other words, that could be that we are getting misled by studying examples from string theory to give general principles, and that is wrong to do because you're just looking at a very small, specialized subset. And that's the attitude that...
So you take the n equals 16
Yes?
case.
Yes.
You say the rank is limited to 22.
Yes.
That's a string theory argument.
No. That's a non-string argument agreeing with string theory.
Anomaly argument?
It involves a combination of distance conjecture, duality conjecture involving extended distance conjecture, and anomaly inflows on the strings. So it's a mixture of anomalies and distance conjecture.
Question. See, the distance conjecture is a conjecture based on string theory.
Yes, but not based on theories with 16 supercharges. It's based on string theory examples.
But I think what Juan is
Yes.
saying roughly, I mean, and I agree, is that one should be a little open-minded about other healthy places.
Absolutely.
Healthy theories.
We should be looking. I'm not saying we should
Where
not.
some of these conjectures are false. So there's another avenue where you
Yes.
try to take one of these theories, relax.
Yes. So I will say I'll give you exactly an example of the type you're looking for. So part of this distance conjecture suggests, and the same thing that it's motivated by string theory, suggests in the context of ADS, you cannot have just an ADS, let's say ADS 4, purely flat or essentially flat, one big ADS. You cannot have it. In string examples, indeed, we have an extra ingredients in them. However, that can be proven false. How do you prove it false? You construct a conformal field theory with big enough gap, which you prove it exists, and therefore disproves the conjecture. If you can construct, so exactly. So in fact, Eric gave a talk, Perlmutter gave a talk earlier last week, exactly about asking these kind of questions. So I would say yes, there is a possibility, and we should look for them. Absolutely, we should be open-minded. We should try to find them. The more we look for them, the more better we understand whether actually these are correct principles or not. So far, interestingly enough, all these ideas seem to suggest things which is either hard to disprove or potentially correct, or something which we don't know or disprove. So this is going to be hard. So it's interesting that exactly lands you on the questions we don't know the answer to. So I would say that at the very least it's motivating questions of would-be systems which has nothing to do with string theory a priori, which we are predicting cannot exist. So we are making predictions about possible conformal field theories, nothing to do with string theory per se. Those are extremely exciting. And it could be proven wrong, exactly as you're saying.
Sorry, could you come back quickly to Juan's comment? Because I want to specify. Yes. I mean, is it right that you are trying to tell us that we should maybe rethink or come back to Coleman?
Yeah, that's what has been discussed in the other program.
Another landscape on top of our landscape.
Yeah, actually the example he brought up is very interesting because it's just an axiom and say no potential. So in string theory we say, well, we have objects that induce a non-perturbative potential, we have instantons, and if we have wormholes are part of the guys who give a potential to instantons. So you could have any particular theory would have an instanton potential, but if you sum, as Coleman suggested, over the wormhole contributions, you could go to different ensembles, and one of them might be one with absolutely no potential, a flat direction. The underlying theories all satisfy the weak gravity conjecture because they all have instanton contribution, this wormholes contribution. But if you change your framework of not having a single theory, but these ensembles that are being suggested in the other work.
I'm actually, one should study all possibilities. I would say that I think that the context of ensembles, I would think that studying string black holes that we do understand, like the kind of things that were studied in 4D or 5D black holes, we already have a good picture. Understanding those and how that fits with the ensemble, to me, is the right picture. Whether it's a Fuzball picture or something, we know that the idea that you have this ensemble of would-be black holes is captured by classical gravity already is true within nothing amazingly exotic. So I'm not convinced, actually, we have to change the framework, actually, to be honest.
Right. So I wanted to ask about the averaging of theories. So even if there are some things that you can compete, which are, go to different ensembles, I mean, at least in higher dimensions, whenever we make an experiment, I guess we should be in a particular alpha state, right? There should not be mixing between the different alpha states. So even
This
if
alpha state could have a flat direction, for example. One of these alpha states could have a flat direction for the axion.
Oh, you're saying one of the alpha states?
Yes.
Okay.
So it could be possible that we live in a universe that, the model is this average that does not satisfy the constraint, but is an average of theories, or we should live in one of the theories?
Well, that's one question. So what is the right thing to do for cosmology? Is it to consider it in the alpha state, or is it to consider the theory as being the average, and only now we start measuring and we project, right? It's like the cosmological fluctuations. We also, in the beginning, they were all together, and then now we are selecting into some particular subset. So
sorry,
I think this is the... Yes.
I thought that the different alpha states were in different superselection sectors, right? So if we pick, at least we're going to be in one of the alpha states, right? So we can compute whatever, but we're going to be
Yes, but the idea is that the simple theory, the theory that is supposed to be inconsistent, might give you a measure on all these alpha states and which ones are more probable than others, and so it might have some use.
But if we should live anyway in one of the alpha states, it means that we should satisfy these constraints anyway.
Yes.
Yes.
So I don't think that even if it's Coleman's picture, I don't think Coleman didn't say that writing the effective field theory would be invalidated with these ideas. So I don't think that is the...
Well, my point is simply that in the other program we're discussing some theories which naively we would rule out. They are inconsistent, they have some problems, but then they are reinterpreted in terms of ensembles. And in the context of ensemble, they have a perfectly nice description. Now, you might write this off as a curiosity of two-dimensional physics, but it is an example where the gravity theory has incorporated all the non-perturbative effects, and incorporating the non-perturbative effects turned out to involve this ensemble.
That ensemble is different from the ensembles of the type we see in 5D black holes? I want to see if he agrees with that, because that's not my interpretation. For example, Steve's, in my discussion with Steve, his view is that this is actually telling us Fuzzball picture is maybe the correct picture to go. If that's the case, I'm not sure in what sense this is the...
I'm not willing to say yes or no to this question. So I think, well, it's been discussed, so I don't know. But it is an ensemble of coupling similar to the one that Coleman was discussing, the Coleman and Giddens and Strominger. And I mean, in our discussions of string theory, the kinds of non-perturbative effects that we normally consider are rather limited. They do not include these big topological fluctuations of the space-time geometry. And so you could say, well, maybe this is a lesson we are learning in 2D where we can solve it, and then we should see what the proper lessons are in higher D, or maybe higher D is completely different. I don't know. I don't know what the right lesson is.
Well, I would say
What
that...
sense is JT gravity by itself just inconsistent?
I don't understand that statement either.
Well, just to make it a little more clear, we could have JT gravity together with, let's say, U1 gauge field. Right? That is something that has an interpretation in terms of an ensemble. But this theory would be in the Swampland because it doesn't have charged particles. It has the gauge field.
No, 2D, Juan, you're misinterpreting. 2D can have global symmetries. 2D worksheet has global symmetries. That's against all the principles of Swampland, you might say. Forget about, you don't have to go to JT.
Okay, fine.
So 2D is not, you're misleading it. 2D is a very special case where gravity is boring. It's not the kind of thing we're talking about. So you shouldn't base a general statement based on JT gravity.
Okay, fine. So 2D is a theory where presumably those 2D theories that have global symmetries, it's likely that maybe can be interpreted as some kind of ensemble.
Okay, that's fine. I don't have a problem with that, but that's not interesting for our universe.
Sorry, I think JT gravity cannot have global symmetries. Because you have this two things that have the number.
But in order to have the global symmetries, I think you need some extra feet, so it's not purely JT gravity.
But going back to the alpha ensemble, in string theory, one of the Swampland statements is that there is no free parameter.
Yes.
Every parameter is the expression value of field.
Right. Yeah. No, I know.
So if you are saying that's indeed false, this is against everything we have learned in string theory.
Well, it's false in 2D. It's interesting that this false in 2D. Now you can say, well, okay,
2D is different, in fact, exactly.
It's different, but the near horizon geometry for 4D black hole is 2D. So there is something to understand, I think.
But so related to this, could it not be in higher D, in the context of Eric's talk of last week with the CFT bootstrap, that the suggestion is that we should actually integrate over a conformal manifold of a CFT, and that's the ensemble we're looking at, and then maybe such a thing would not, ADS gravity with an axion would not be in the swampland because you cannot say bootstrap it away. Because that's the ensemble. You really have to, averaging over couplings, in this case would be averaging, say, over a conformal manifold.
Well, in the context of ADS CFT, we don't have to average anything. Specifically, we have a conformal theory and you have a dual description. So I don't think that at least the basic bulk of the...
The problem is that in ADS CFT, once you allow geometries that connect different boundaries, it seems that you have to average. And I think there is a big philosophical contradiction between the other program and this program. I think it's an opportunity to understand, what is...
I don't see the contradiction. I mean, I think it's very
It's a
interesting.
tension. Well, let me call it the tension. Like it's a philosophical tension.
But still, I mean, maybe one has to be careful of how to, when we say something is consistent or inconsistent, that I agree can be that tension. But if we are wondering what effective field theories in the infrared can describe our universe and can be UV completed, the UV doesn't change, because since our universe has to be one of these super selection sectors anyway, it means that the effective theory that we observe has to be set. Or maybe I'm missing something.
So the point is that
It only has to, sorry to interrupt, I think it only has to be a super selection sector once we measure something that depends on that parameter. But it might be that the effective theory describes the idea of a universe. No one has measured that parameter, and it could be all of them. So.
Depends on us on this Earth.
Well, I don't know. I don't know what the proper.
Well, I don't think there's a philosophical disagreement. I think the 2D story and higher D is not the same. That's number one. I think it's a crucial difference. We have encountered this in many examples in Swampland. So 2D, we should not draw a general lesson about higher D. Secondly, I think that it would be good to export, as maybe a suggestion from the Swampland program to the other program, would be try to import this to higher dimensions and see what the regular black hole looks like. We cannot say that the count of the black hole entropy was just a fluke. We have no fluke. So therefore, all this picture that we have understood about the black hole, the unitarity in the context of regular string theory, holds. We didn't need anything exotic for that to be the case. So that, to me, the statement that we need something amazing, exotic, otherwise we'll not be able to explain anything involving quantum gravity is a bit strong statement. In 2D, the story might be different. There's, for example, the existence of the alpha vacuum and having the alpha as a parameter is against everything we have learned in string theory, to say for free parameters.
Well, that's the philosophical tension.
It's not. No, I would say it's a philosophical tension with the rest of the string learnings. We have learned in string theory that the very first lesson we learned in string theory, there are no free parameters. You're going against that. That's really strange.
So, could it be? So you seem to be kind of like assuming that this picture, the fact that you can make ensembles of theories, is gonna kind of like wash out Swampland constraints. But I guess it could also work the other way around, right? It could be that the fact that you can look at these ensembles of different theories and correlation give you more constraints, right? I'm just asking if it's possible.
Maybe, I don't know. I think it's...
Yes.
But maybe just one comment. These geometries that connect two different Euclidean boundaries, they exist in any number of dimensions.
Right.
So you can make it very sharp in 2D, but they exist in ADS5, in ADS6,
Yes.
ADS7, whatever you want. So there's still a question of how the old school microscopic ADS-CFT is going to explain those geometries. And you can ask...
Yeah.
Such geometries have many negative modes in higher dimensions. So it's unlikely they contribute as valid saddle points.
But Thomas, that does depend on the boundary conditions, right? It depends heavily on the boundary conditions in ADS.
Yeah, sure. It probably depends on boundary conditions.
I have a question. Do we understand Euclidean quantum gravity or the model Euclidean quantum gravity for the real world gravity well enough to be certain that in higher dimensions a process where a baby universe bubbles off is actually allowed? I mean, possibly, we all know this process needs a singular point, a point where the Lorentzian metric becomes singular. And I've always been worried, and I don't know whether people understand that in high dimensions, in 2 dimensions, the CFT allows us to avoid this problem. But maybe in high dimensions, this process simply doesn't happen. I'm very much in favor of wormholes, but I'm worried about this point. Do you have an answer to that?
Not completely, but the recent discussions in 2D have highlighted the importance, let's say, of off-shell geometries that connect different topologies and so on. And you can have two ADS boundaries, and you could have even an off-shell geometry connecting the two. Do they give any They seem to give some kind of correlation. Maybe they all vanish for some reason, but if there is a reason why they vanish, it should be interesting.
It's all Euclidean.
It's Euclidean, yeah. The discussion is Euclidean.
But what if, I mean, the question is whether the Lorentzian metric tunneling process, which is supposed to be described as a Euclidean model, is really possible. I mean, to me, this analytic continuation.
Well, I don't know. Maybe that's the way to understand what these vague universes are in Lorentzian signature, to understand how that.
So you're saying Euclidean defines a theory, also in high dimensions?
It might be that that's the way to think about it. I don't know what the correct way to think about it. I'm just.
Sorry, Juan, when you say that offset geometries contribute to this thing, you mean that there's no saddle in that topological sector?
Right. Yeah. There are examples where there are no saddles.
Well, it's an endpoint.
It's the endpoint of the path integral that contributes.
Any other comments, or could be separate? I mean, no ideas, any discussion topics.
So related to what you said about phenomenological applications, like I very much agree that not enough attention has been paid to like the interplay between these two things. But I feel like I think crucial to being able to discuss this is two things. I feel like we haven't really decided whether these criteria, whether they need to be applied to say like the UV phase of theories, or to the far IR phase of theories, because I think as we were also discussing the other day, some of these conjectures apply to in the UV. There are all these tricks you can play, which apparently there's nothing wrong with them. That they leave you with like an IR theory that seems to completely violate all these some of these conjectures, right? Like the Gabri in particular. And that goes in the direction that I think, in order to be successful to apply this in phenomenology, like some of these things also need to be made more quantitative. And I think some more effort, that also requires, I think, more attention. Like, all these questions about, like, for the Gabri conjecture, like, how sparse, the sub-lattice has to be and things like this.
Right.
Like, getting even, bounds on this.
Yes. Well, at least my feeling is that this is always an IR statement. That's the safest way of viewing it, in my opinion. But there could be pushing it to the UV. That would be interesting, too. But I agree with you 100% that we need sharp statements. And that's a good point I should have perhaps mentioned. This in the context of weak gravity conjecture. It's something that we are making sharp statements. Well, not exactly, because the number is sharp, but the charge quanta is not sharp enough. So we have similar examples, and I will give you a number similar to that. For example, what is the maximum rank of a gauge group in n equals to 2 supersymmetry 4 dimension? Is there a maximum? I think yes. What's the maximum? I don't know. In 6D, the answer to 1, 0, mathematicians have told us what's that maximum rank they can give us using LFT Calabi-Yau. We don't know if there's any other way to get the quantum gravity 1, 0, but I suspect probably not, in which case we have a maximum rank. So there are sharp numbers. So that at least in the 60, 1, 0, there's a sharp number they have given us, which we cannot yet prove if it's actually correct. And so, yes, so the question is coming up with techniques to say you cannot have more than this number of particles. Why? What's the reason? We have to figure out.
Can you clarify your statement that these should always be IR considerations? For example, obviously if we go to energies below the electron mass and integrate it out, then it looks like we have a theory that violates the weak gravity conjecture. So
sorry, what do you mean?
Well, if we integrate out all of the charge matter.
Oh no, sorry. The statement is that the mass goes like charge. You have to go enough to that mass to figure out that there is a charge, of course. If you go to the mass equal to 0 sector, you don't see a mass, positive mass, that's for sure. So, that's what
But there may be also a statement to be made in those cases, right? Like, so when you integrate this, the electron out, you generate Euler-Heisenberg-Lagrange.
Yes.
So maybe in the deep IR, you could make a statement about the coefficients of the...
Yes. So the way to say it is that in the context you just said, you can go to deep IR, in which case the weak gravity conjecture doesn't say anything specific. You just say that because the mass is higher than that, so you have to put a cutoff, so you won't see it. There's no contradiction. It will be very less useful in the deep IR. So yes, you have. So I agree with you that you need to include some ingredients from what would not be the deep IR, like the mass of some states, in order to make interesting statements. That I agree.
So IR should mean I have access to the entire spectrum.
In the IR. So I meant that if I
in the IR specifically below GM Planck.
Yes, with some cutoff. Yes.
I mean, a gauge you want without any charge matter. What does even G mean? Then how do you know that?
Wilson.
Sorry, what was the question?
Like, what does G mean?
No, I mean, say the answer is the extremal black hole. So as soon as you have the coupling to gravity, then you just say, I will just figure out what's the extremal black hole. Weak gravity conjecture is an inequality involving the extremal dipole. Yes.
If 2D is special in the whole swampland discussion, does that also imply that if I go from 10 to 2, that I should be able to violate swampland bounds?
2, you cannot freeze the moduli. So in some sense, yeah, I would say the following. In the case of 2D, the fact that all the string vacuums seem to be connected, at least that's one of the Swampland conjectures, the cobordism class is trivial, it means that there's a unique theory in some sense that there's a wave function of 2D, there would be sigma model in 2D which describes that one. Is unique. It's not the ones we are thinking like in the worksheet. So there seems to be a distinct class involving worksheet description of a quantum gravity, which we have in string theory, versus what you get by compactification. The two seem to be disjoint, as far as I can see in 2D.
And then this string lamppost principle, then you have several disconnected.
So in the 2D, again, I would say that would be yes, because we already know there are disconnected 2D theories. So that already we know that global symmetries are non-trivial in 2D. We do have consistent worksheet theories, which is the quantum gravity in 2D, which have global symmetries, current algebra. So yeah, we have already, if you wanted to go that far, we already have quote-unquote disproven swampland in 2D. But I guess that's not the right criterion in 2D. I think again going back to this question that Dave asked, I think one of the most exciting things connected with holography and ideas is exactly the ADS-CFT link. And because these ideas make contact with ADS-CFT, and specifically in the case that suggests that ADS-CFT involves always extra ingredients and pure ADS is not allowed. And so that's a very strong statement. And it could presumably be falsified, if it's incorrect, by construction of models. And I think that's a golden opportunity, I would say. If it's true, it would be extremely interesting to see that this kind of ideas, which are motivated from things that have nothing to do with holography, to tell you something about holography. And if it's false, it would be good to know and bring it back. So I think that's, I would say, a kind of question we should focus on, to try to find counterexamples.
Yeah, so for example, pure ADS3 is believed not to be true. Correct theory, and there are some, you can do some calculations and you find some problems. But you find the same problems with pure ADS2, so just JT gravity. The same problems with, if you try to say that pure ADS2 is dual to a CFT or to quantum system, you have some problems. But then when you interpret in terms of an ensemble, it makes sense. So it might be that some of these theories have other interpretations. Maybe gravity is smart.
It certainly would be good to see if ADS2 could be made sense out of that way or not. But certainly the canonical connection between holography would suggest that there should be, or why not, a theory with a huge gap, and what prevents it? From the CFT perspective, it's not obvious.
I find interesting that in 2D we have a non-canonical connection to holography. And
that's an interesting one, but still there could be canonical ones. I mean, the bulk of the examples we know in holography are the canonical ones. So before we go to the exotic non-canonical one, we figure out what's going on with the canonical one. Seems to be prudent.
But if you start adding wormholes to the canonical ones, you might get in trouble.
Well, nobody says we have, even in the context of ADS-CFT, we have understood everything about quantum gravity, that's for sure. So you could have interesting things similar to the JT arising in 2D to higher D. I'm not debating that. I'm not saying we have understood the quantum gravity fully in ADS case either. But the connection between CFT and ADS, we think we have a dictionary, and we have, in those cases, we have good control. So I'm saying the way to check these without saying, oh, you're assuming string theory is true, you're not learning anything. No, there is a way to disprove it. You just go and construct. Very pragmatic, very concrete. And indeed, the fact that it's difficult in the other language is interesting. That's not a trivial thing to settle. So it should be interesting to study those kind of questions.
So I think a related interesting question is that there are many of these conjectures that seem to be based on having an Einstein gravity description. So to what extent this Swampland program is constraining consistent theories of quantum gravity or constraining effective theories with a weakly coupled Einstein gravity description, no? Like
yes.
Where Einstein gravity comes into the game or not. I think that's also...
Yes, most of the discussions are based on Einstein gravity. For example, higher spin theories and all that are examples that are different. You're right.
So that when we say consistent, I mean...
We mean specifically about the Einstein gravity.
Exactly.
So I think that even, for instance, the weak gravity conjecture is not true in Vasiliev, right?
Yeah.
In ADS regions.
So we are talking about specific ones. Yes, correct.
So can I ask? Can I go back to the study with the wormholes and the averaging? Just a second. So,
so the two programs are interacting. Go ahead. We have someone who's interacting nicely.
So is it clear that all the things like black hole evaporation work in the same way when you have an ensemble? And does everything that usually holds also?
Well, there are these two. My view is that there are these two-dimensional gravity theories where the ensemble is important. Where the ensemble is important for all cases is not clear, and it seems to me that in very specific gravity theories, let's say n=4 super YAMLs, I don't see how they can be an ensemble because, well, I have this conventional understanding that that's a unique theory. So if you wanted to interpret it as an ensemble, you would have to imagine that there are lots of n=4 theories, and that
can you average over?
And that you are averaging over them, and this sounds unreasonable to me. And so anyone trying to defend an ensemble for that would have to have a hard time proving that. So the extent, I think, understanding this ensemble and when it's relevant and when it's not relevant it seems important.
But assuming if the ensemble approach applied to more than 2D, you would agree that then you would not have a unique quantum gravity theory. In other words, this idea that you have parameters or global symmetries would be again an issue and so on, because you can promote these. If you cannot go from one alpha to another one, if you go to super selection sector with one alpha, the other one would be disconnected, a different alpha from the. There will be no fluctuation where you can create the other alpha in your universe.
Well, these examples, even the 2D examples, they involve some asymptotic. So you have some gravity theory with some asymptotic boundary conditions, and so the gravity theory depends on this. Or the ensemble, or your averaging over, and so on, depends on those asymptotic boundary conditions. So that's similar to the conventional framework where the vacuum depends on the asymptotic boundary conditions that were in string theory, like ADS.
But these alpha parameters, what if you would view them as a web of a field? They would have infinite mass or finite mass? Because that's the question. Can you fluctuate them locally or not?
Well, the idea is no, but I'm not sure in this case.
Because that would be extremely interesting, because all these ideas in string theory suggest that there's a uniqueness of vacuum and all that, says that this is not possible, except in 2D. And exactly in 2D that's possible. So that suggests exactly the loophole is in 2D. So if you think that the 2D can be transported up, it would be extremely interesting for the whole string theory. I would say to have any statement that the fields are not parameters are not web of fields is a completely revolutionary statement in the full string theory. So regardless how else you get it. So, and it's against everything we know in string theory, I would say, except 2D. Yes.
Just a quick question. So you said 2D is special.
Yes.
Then at some point you said 4D and higher. So where does 3D?
3D is more. Okay, I wanted to make sure. I want to make sure what I'm saying. 3D is always. I'm a bit confused whether I should think about the Einstein gravity as dynamical in some form or topological again. So morally, 3D should also be included in that list. But I always want to make sure. So I said 4D and higher.
Morally, it should be included where?
I would say in the discussions of Swampland, but there could be 3D is close to being. There's no reason that I have a counterexample. I'm just worried that there might be some aspects of that is different from the rest because it's, the dynamicalness of gravity is not there in 3D. It's kind of more topological, so it's borderline.
Yeah, I mean maybe that's a good place to try to connect this to averaging because 3D is also
3D case. I would say 3D case. The global symmetries issues, I think, would be still an issue, probably in 3D, but yes, but I'm not completely sure. The 3D case is a borderline case. I'm less sure about 3D. 4D and higher is what I'm more sure about.
And the statement of no global symmetries, that one we expect it to be true beyond Einstein gravity, right?
Well, it's motivated based on black holes physics. And so that motivated the fact that there are no such thing as disconnected universes in quantum gravity in higher dimensions. That's the motivation. So I would say that's one of the things we doubt least among Swampland principles, the lack of global symmetries.
So, for instance, the Uri-Harlow argument in holography also works.
Yes. So for example, Harlow and exactly, and Uri's argument in holography suggests the same. So it hangs together, I would say. Any other topics to discuss? Yes.
So I wanted to ask, I mean, it's related to the explaining it part of it, right? So whenever we have So out of the 4 principles that are listed there, only one defect has given us really arguments for strong versions of the conjecture. Going back to this discrete parameter or whatever. So basically, I would like to understand if there's any reason why it seems that just looking at higher things like black holes or unitarity doesn't seem to give us arguments for strong forms of strong line construction, only mild forms, and relatedly, if there could be any black hole or high argument for some distance conjecture. I just want to hear anyone.
Anybody has comments on that? You want to ask if black hole or something like that can explain distance conjecture?
Yeah, or any strong form of conjecture.
Well, strong form of which conjecture?
For instance, with gravity conjecture, like as you were saying, the charge quantum, we don't know what it is.
Oh, a value. Yes. No, I mean, these are very good questions. I mean, we know from examples in string theory that should be the case. Right. Like there should be a sharp bound. There's a number, 255, whatever, 491, right, or whatever. There's a particular number, which 6D we know, that cannot do anymore. Why? We don't know why. So we don't have a deep enough understanding of quantum gravity to say a priori that should have been the number. But I think we are beginning to develop tools like studying defects. I would expect unitarity mixing with defects, perhaps with holography, with a black hole. Putting them together might have interesting implications. Some of them are already coming out as giving you strong restrictions, which is consistent with what we know in string theory. So distance conjecture that you mentioned is particularly difficult because it has almost zero motivation based on black hole physics or other arguments of quantum gravity, but we have very strong evidence based on string theory. So I agree that that's one of the areas where we really need to do a better job to try to explain it. What's the principle for that? Yes.
This is a question about this, and I probably am wrong, but wasn't one of the ideas behind Dieter Lust's talk that you actually connect a attractor mechanism, where you actually end up in an ADS2, but then the size of the ADS2 is the size of the S2, so it measures the entropy of the black hole, that somehow in this way you can make a connection between the distance conjecture, because the entropy might count this tower or not.
No, I think that in the context that Dieter was talking about, the ADS2 distance conjecture, in that case just means ADS2 by itself is not that there's an S2. And if you make ADS2 big, S2 gets big, which we know. So it's kind of, I don't think you learn much in that case.
So I think another way you may, so regarding this, explaining it part, there's another way that I think hasn't received much attention, which is we do have, field theoretic toy models of the Swampland in the form of, theories that have some form of gravitational anomaly below some scale. So I'm thinking, the only case I thought about in detail is, for example, say, just take for the U1 gates theory, and the infrared fermion spectrum has a gravitational U1 anomaly. Okay, so we know in those theories can be consistent if the photon is massive and the theory has a certain cutoff. If you take the photon mass, if you try to take the photon mass to 0, that will be inconsistent in the sense that at some point, that constraint comes from the gravitational anomaly, so you will be sort of going into the Swampland. So I think just looking at those two examples and see what happens or what goes wrong as you take that Swampland limit, I think that can also be interesting. Like we thought about it in the case of 4D U1 gate series with U-grand gravitational anomalies, which are also special to U1s and 4D. And for example, taking this limit of a very light photomass forces you to introduce a large number of species, and if you also have pure U1 anomalies, you get this quantum gravity cutoff to the g to the 1/3 and Planck, so with gravity conjecture scale. So I think, probably doing this in higher D, where you have things like defects and all other things which are not just fermions, that could also be interesting, I think, in the spirit of trying to have some ideal motivation.
Yes, I think it'd be interesting to study. It would be effective theories and try to see what could go wrong and checking what we know in string theory in those contexts. So I agree. Yes. Yes.
I have a question, probably relevant only for part of the audience, because if you believe the zither cannot be realized, metastable zither, it's irrelevant. But if something like metastable zither exists, there's this opposite views that the zither is a finite quantum mechanical system, or that you should think of it somehow more along Wheeler-de Witt, wave function of the universe, or some totally different point of view. I mean, is there some kind of predominant modern point of view? What is the view of the community on the zither as quantum mechanical system? Anybody has an opinion on that?
Well, people have said, like Lenny has said, de Sitter is an exotic object if they exist in a fully stable one. So I don't think anybody thinks de Sitter exists quite stable. So you're talking about metastable.
I'm talking metastable.
In which case, the difficulty would be exactly quantum duality is usually hard to imagine exactly. So people have talked about, I don't know, G wrote paper. G is not here, right?
Let me be specific. I mean, specifically, I want to know, I kind of share the opinion of de Sitter being a finite system. It seems to be logical. The horizon is the end of the world.
Yes,
right?
yes.
But then this thing can presumably tunnel to Minkowski. And then suddenly you get this infinite system by tunneling from a finite quantum mechanical system. That seems to me make no sense for me. Am I naive about this contradiction? What do people think?
Well, it could be that you have some bigger theory which has an infinite set of states, right, which are Minkowski or whatever, but you're locked in a particular set of states that mix with each other. And
But then the system is not a finite system.
Right. Well, it's not a finite system, but to a very good approximation.
Finite subsector.
Brahma looks like
It's a finite subsector, he was saying, yeah.
Okay.
Yeah, and also in the Sitter, like even if you take the point of view that it's a finite dimensional quantum system, the fact that from the static patch you get the horizon seems like it's an open system anyway, right? Which is also interesting.
Yeah, that's a different point of view, though.
Right. You could think of it in global coordinates or in the static patch, right?
No, but shouldn't only one of these points of view be right?
Why? It should be. Why couldn't it be both? I mean, you could have a finite dimensional open quantum system. That's what it looks like in the static patch if you take seriously the fact that the entropy is finite.
Okay, I have to think about that.
Another question that I'm very much interested in is to what extent could you think of the Sitter, the entropy that you see in the static patch, you see a horizon, right? So to what extent could you think of that as an entanglement entropy, which could connect the static patch and the global picture, right? From the global picture, there's no horizon. Well, I mean, there's also a horizon, right? But there's this finite dimensional system, which has a natural Bell partition, and there's a horizon in between.
I have a question, which was triggered by the previous one, which sounds like it's partially, or one facet of the question is there a meaningful, or can there be a meaningful quantum gravity in compact spatial universes? So basically no boundary. How much of the Swampland conjectures really are anchored in the viewpoint that this theory, whatever it is, has to exist with some asymptotic region where charges can be defined and so forth?
Good question. Most of them are based on, as I said, like the bigger than 2. So in particular means macroscopic dimensions are not 0. So you're asking about 0 macroscopic dimension. But you're compactifying the whole space.
No, just closed universe.
I know. But that's equivalent to compactifying into nothing, in other words.
Okay.
Yes. So effectively you're saying that we want to have no macroscopic leftover space as part of the discussion.
But it could be our space.
It could be
but,
macroscopic.
let's say we live on a very big torus, right?
Yeah.
No, I know. Big to me, infinite is the only thing which is big. So you can have arbitrarily big, not measurable. I'm not talking about physically measurable statements. I'm just saying infinitely big is what people have assumed when we talk about various criteria. So if you want to have, strictly speaking, compact, which means it's not infinitely big, even though it could be huge, yeah, I understand, then for that, I don't think people have, I mean, we still believe locally you should be able, if you are able to disentangle a piece of that to push it to be like RD or something, yes, the statement should be locally applicable and so on, but I don't think people have specifically talked about it. I don't think anybody believes it shouldn't exist. At least I don't see any problem with it.
So one question
Can it relax the Swampland constraints, basically, as well?
But the difficulty would be that if you're allowing the whole thing to be compact, which means that you should then allow arbitrarily small or large in that compact geometry and so on, then it could be extremely fuzzy, it could be extremely Planckian, and as well as big and so forth, and you have to, you will not get you cannot stabilize it. In other words, you're not going to have a specific geometry. So there's, in other words, usually the non-compactness gives you an anchor to stabilize the geometry. Usually you have a boundary condition, you have something which stabilizes. Yes?
I don't get it. I mean, you've been emphasizing that a lot of the Swampland constraints come from studying black holes.
Yes.
Extremal black holes.
Yes.
You can put an extremal black hole in closed universe.
Yes.
And the universe can be a million times bigger than
So I would say that people phrase it in the non-compact case to the extent that a huge space which is compact can mimic locally the non-compact one, then you should apply presumably, which is the context you're talking about. So when I said people haven't said, I meant they haven't said anything specific about the compactness. If you assume that this principle that local aspects of geometry should be applicable as if it's infinitely big, why not? Then could be. So people haven't thought about any specific things that proves that.
You can there's a notion in which you can stabilize a totally compact spatial universe. This was pointed out in a paper by Al-Kami Hamed. And what effectively happens is that the scale factor bounces back and forward, so it grows and it shrinks again. But if the three-dimensional part of the space is large, you don't see it. I mean, it looks like an ordinary cosmology. So I don't see how it's inconsistent with normal Pauli effective field theory, where you assume actually a non-compact spatial universe. It should kind of give the same physics.
Also, since in quantum gravity topology can change, I'm not sure that the statement that you have a compact universe like forever is, it's really so sharp, right? I think that after this discussion, we're going to have a talk about precisely that, about having like a compact space and then, floating ADSs that can connect and disconnect with. So maybe you could, if you want to make some argument about something which is compact, maybe you could just start by, putting by hand something non-compact to it and then can connect or something.
It would be extremely interesting if you theoretically assume our universe, let's say, is a compact torus, and that could give you an anchor to some of these which you didn't have otherwise, and you have some processes that you wouldn't have thought about. It would be extremely interesting. People haven't used it. It doesn't mean it cannot be there. And similar to the ideas that in these island ideas that came, that was global topology was crucial. Maybe it would be important to illustrate some of these. I have no idea. It might. I think it's worth thinking. So. Yes.
So regarding the sitter, I wonder. So it seems that at least asymptotically, like near the boundaries of field space, we cannot get the sitter. We have many no-goes. I mean, I don't know in the middle of the bulk, but
yes,
at least asymptotically. And I feel that we don't have a very well understanding of why, because I agree in supergravity we cannot have it, but in the string theory we have more ingredients, and in principle we could have, I think, obtained some de Sitter asymptotically. And I don't know, I wonder if someone has some intuition of why we don't find it, because I feel that if we don't even understand why we don't find it in that case, I mean, how are we going to understand if it's possible at all?
Isn't the paper by Gary and Cumrun and Oguri and Pauti, isn't it giving the reason? Like thermodynamics plus the distance conjecture seems to imply this.
Well, it's related to Maldacena-Nunes no-go theorem, and so it's kind of, in all these constructions you have a large radius or large thing, and in those cases you can rule it out. And so you are saying that yes, we can even rule it out in cases which are not necessarily completely obvious what geometry they are, but based on general principle. But I think that there would be, you could view it as a further evidence. So you could say that why should Maldacena-Nunes theorem even exist? That's a good question. So that you would say that why should it have been there? Why did you have to go inside? Why weren't they able to construct the counterexample already? Yeah, that's a good question. It just wasn't there. I don't know if one has a take on that or not.
So a related point to that is that we cannot get, for instance, the Sitter there's a theorem you're going to get the Sitter in perturbative hydraulic string theory, which is
yes, which is exactly. So that was the example that Mariana mentioned.
Right.
So already surprising. It has nothing to do with geometry. You can go to highly curved heterotic backgrounds, and the proof is that as long as you're in weak coupling in string theory, it doesn't work. So it's not like crazy geometry will save the day. There you blame it on heterotic string coupling constant, perhaps. So there's some blame somewhere. You can push it somewhere else.
Is there a similar statement for type 2?
So by the way, I would say that continuing that discussion, some people generally say that quantum corrections could give the answer, and which of course nobody can rule out because it's hard to have a better understanding, especially if you're going in the middle of the region. We don't have control, so it could be, I don't know, it's a no man's land, so to speak. But weak coupling, I think the consensus seems to be that it's going to be difficult. Now, whether you view KKLT as weak coupling or not is the debate. It still goes on.
Weak coupling doesn't mean necessarily string.
No, I know. So the people are still debating that discussion, that point, whether or not we are at weak coupling or not. What do you mean by weak and so forth? Do we trust G string is 0.5 or something, or whether n is what is exactly n? So people are. I mean, so that's the nature.
That's because, like when I was studying with Thomas, like the different points, like the different limits in the compensation model space of F theory, many of these points are not weak coupling. Like I mean, it's really strongly coupled, but still. It's like an infinite distance limit,
yes.
so you would obtain the same result.
Yes.
That it's
So,
not tied to
related to that statement is that you're right. So what appears as quantum correction to somebody could end up being
So
classical geometry, maybe
those
exotic
points
for another one.
From a mirror
Yes,
one,
yes.
they have
That's one of
quantum
the things that
corrections, they have-
the notion of quantum correction is not engaging, is not duality invariant statement. We know that. So when people say quantum correction is going to save you, they're talking about a very specific frame. In that particular frame, the quantum correction of that frame. But why should it be that there's no frame for which those things are classical? So it seems that there's no description in which everything can be classical.
I will comment on that.
Yes.
So there are some things that are not true classically, that are not possible classically, but are possible quantum mechanically. So for example, the traversable wormhole. So it's a classical no-go theorem that forbids the traversable wormholes. But if you have, I don't know, but you can stabilize them by including suitable quantum corrections.
Like Casimir energy and things like that.
Yeah, stuff like that. So that's a concrete example, and it has to be quantum. So it's just not possible
Yes.
classically for some dual observer and
Yes.
so on. So.
Yeah, but no, the point is that the Casimir energy could be dual to something which is classical.
Well, so we could ask this. So for example, in those cases, sometimes you can use, let's say, conformal field theory. The conformal field theory has a gravity dual. Then what happens is that you have a similar configuration, but it's not topologically non-trivial. So
Right,
in order
so-
for the topologically non-trivial
But classical,
solution,
yes.
you need the quantum correction. And,
Yeah. So what she was referring to, Irene, was that there was these no-go theorems for the case of the hydraulic, which includes these non-trivial
Yeah, no,
topologies, and that still didn't help it. That was the context.
It's not quantum in.
I have a remark about that. I think there is a notion in which you can distinguish quantum from classical, because even with dualities, in a very practical terms, the scaling with respect to some string coupling and to a volume will always be, say, power law, polynomial for classical, but things that scale non-polynomial, like the Gaugino condensate KKLT, there's no way by changing duality frame that you can classicalize it.
No, that's not true. In fact, the paper we wrote with Robert was exactly doing that with Dijkgraaf. We classicalized Gaugino condensation. That's one of the well-known examples, which when the KKLT originally wrote the paper, I said, why don't you go to a dual frame which everything is classical? That was my objection to KKLT originally.
Here's my point. Can we distinguish quantum corrections that can never be
This is
classical?
so if you write the omega wedge F as a potential, superpotential, that could be the dual type 2B version of Gaugino condensation. That's exactly how we describe all these n equals to 1 superpotentials. That was part of that program where we pursued the diagram. It's all classical.
But if you do that transition, don't you then change the classical flux superpotential that you had originally?
No. He's talking about the case where the Kähler moduli are controlling the Gaugino condensation. I'm talking about the case with the complex structure of condensation. So I'm just saying the statement that the Gaugino condensation by definition is quantum, what I'm saying is that's not true.
So could I just comment on the symbolic no-go theory? If you dualize to F theory, then restricting to just bullshit incidence on the hydraulic side would be completely arbitrary exclusion of most of the instantons. So if you translate that into KKLT or so, or type 2, since you asked it in type 2, if it's completely arbitrary, because these instantons that you exclude by going to string tree level in GS, all are on the same footing in the type 2 frame. So from that perspective, it would be completely unnatural to do that.
Any other comments or discussions?
Yeah, but I want to ask the same thing. Like, how can we distinguish when something is there any way that we can say there is a quantum correction that is not classical?
Is it? Yeah, that's my question. Like,
it's not duality
is there
invariant.
any quantum correction that we know for sure that cannot be understood as classical from another frame?
That's against the duality
Can
principle.
we? I don't know.
But that would be extremely amazing. Part of the way I view distance conjecture is exactly the fact that you cannot avoid duality. H bar goes to zero limit or H bar goes to large limit is exactly that same statement. You cannot distinguish them.
Sorry, but it's also relevant the whole picture. You might be able to classicalize a particular ingredient.
Yeah. No, I'm saying from a given duality frame, of course, what you mean by quantum is clear. But that's duality. That's a frame-dependent statement. That's what I'm saying.
But in type 2, the no-go theorems that are really well understood are always such that there's a duality orbit, so to speak, in which everything is clearly classical. But with KKLT, that's what I think Pablo is trying to say. We invite anybody to try to find some duality orbit, so to speak, where everything becomes classical.
No, I understand. I appreciate it. Otherwise, that would be easy to disprove it. Yes, I understand. But the question I think probably she was asking is that if you're given a theory, are there calculations you could show independently of anything that this says this thing can only be quantum in any frame? That's just like what you were saying, we invited somebody to construct. There's no way that means there's an invariant notion to be quantum. What is that invariant notion? We don't have that. We don't have such a statement. Anything else we should discuss? Anybody wants to bring up any other topic? Okay, if not, thank you for the discussion.